Good morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. Today, we are going to discuss about the energy density spectrum and the power density spectrum. So, the energy density spectrum. So, first of all, you can see what is this spectral density or density spectrum, both the same. The spectral density, it is a distribution of energy or power of a signal per unit bandwidth as a function of frequency. Density spectrum or the spectral density is defined as it is a distribution of energy or power of a signal per unit bandwidth as a function of frequency. In that, the energy signal, the signal which signals with finite energy and zero average power. The signal with finite energy and zero average power. Finite energy means it is in between of 0 to infinite. 0 less than E less than the infinite, and power is equal to 0. Then we can call it as a energy signals. Examples, periodic signals like pulse. Energy signals are always, it is a periodic signals. In the normalized energy, the normalized energy is a simple energy of a signal. X of t is defined as the energy is distributed dissipated by a voltage signal applied across the resistor, and is mathematically the E is equal to integral minus infinite to infinite squared magnitude of x of t dt. We know in the first unit itself, orthogonality function always we are taking by using this equation only. The E is equal to integral minus infinite to infinite the squared magnitude of x of t dt. And the energy of a signal exists only if E is finite in between of 0 to infinite. Okay. We already derived this expression in the last class. The Parseval's theorem is equal to the time domain function in terms of the frequency domain function, the Parseval's theorem, the squared magnitude of x of omega. And also in the normal frequency, the squared magnitude of x of f without having any multiplication factor of 1 by 2 pi is also called as a Rayleigh's energy theorem. The Parseval's theorem for energy signals are also called as a Rayleigh's energy theorem. Got it, my students? Now we go for the energy spectral density or energy density spectrum. The energy spectral density function gives the distribution of energy of a signal in the frequency domain. Energy signal is a time domain function. The energy spectral density gives the distribution of energy signal, energy of a signal in frequency domain. For energy signal, the total area under the spectral density curve, the total area under the spectral density curve, plotted as a function of frequency is equal to the total energy of a signal. It is also called energy density spectrum. Means here the psi of omega, it is in the frequency, psi of omega is equal to the area under the total area under the spectral density curve, plotted as a function of the frequency, is equal to the total energy of the signal. It is also called energy density spectrum or energy spectral density. It is denoted by the psi of omega and is given by psi of omega is equal to squared magnitude of x of omega. You know, in the Parseval's theorem, we derive, or the Rayleigh's theorem, E is equal to integral minus infinite to infinite the squared magnitude of x of t into dt. This is equal to 1 by 2 pi, the integral minus infinite to infinite. We got the squared magnitude of x of omega into d omega. It's nothing but the energy in the frequency domain. The squared magnitude of x of omega called as a psi of omega into d omega is equal to nothing but energy spectral density. Got it, my students? the x of omega whole square. Let the x of t and y of t be the input and output of the respectively of linear system. X of t, the time domain, frequency domain x of omega, y of t, the time domain y of omega. H of omega will be the transfer function, y of omega is equal to h of omega into x of omega by using the convolution relation. X of t is equal to x of t into, or the into convolution of h of the y of omega is equal to x of omega into h of omega. Okay. And in this, y the function is psi y of omega is equal to x of omega is psi x of omega into the h of omega. Okay, the psi x of omega, the squared magnitude of x of omega, and psi y of omega. Then the psi y of omega is equal to, means taking the both sides the squared magnitude here, squared magnitude. The squared magnitude of y of omega is a psi y of omega, as in the frequency of energy spectral density of y signal, and the squared magnitude of x of omega and the squared magnitude of h of omega. The squared magnitude of x of omega in the spectral density, the psi x of omega, the squared magnitude of x of omega, h of omega, sorry. Got it, my students? So psi y of omega is equal to the squared magnitude of h of omega into psi x of omega. Thus, the energy spectral density of the output response of a linear system is the product of energy density spectrum, or the energy spectral density of input, and the square of the magnitude of the transfer function. Means the energy density spectrum, or the energy spectral density of an output response of a linear system is the product of energy spectral density is the square of the magnitude of the transfer function. Got it, my students? So EY is equal to, I already told the E is equal to the 1 by the 2 pi in the Rayleigh's theorem minus infinite to infinite. The squared magnitude of x of omega, it can be placed as psi of omega into d omega, as it is a x, psi x of omega. Got it? Otherwise, in terms of the normal frequency, minus infinite to infinite, psi x of f into df. E is equal to, if it is a ex, ey is equal to minus infinite to infinite psi y of df, or 1 by 2 pi into psi y of omega into d omega. What is the psi y of omega? Let us take here. I am taking the ey is equal to 1 by 2 pi integral minus infinite to infinite psi y of omega into d omega. Okay. If it is a x, is a psi x. If it is a y, means psi y of omega. What is the psi y of omega? We got is a product of the energy spectral density and the square of the magnitude of the transfer function. The 1 by the 2 pi, the integral minus infinite to infinite, the square of the transfer function into psi x of omega into d omega. As we can substitute this equation, squared magnitude of h of omega into psi of. Got it, my students? Here it is a 1 by 2 pi z. If the linear time invariant system is an ideal low pass filter with lower and upper cutoff frequencies FL and FH respectively, then the h of omega is equal to 1. Then h of omega is equal to 1. when the FL is less than the F and less than the FH. Okay, you can substitute the square of the magnitude of the transfer function as a value is a 1. EY is equal to 1 by the 2 pi. 1 by the 2 pi. If I am using the minus infinite to infinite as a 0 to infinite, write it as a 2 into 0 to infinite. Squared magnitude value is a 1 and psi x of omega into d omega. Okay, here also 0 to infinite they substitute because it is not the 2 and there is the 1 by pi on. The 2 get cancelled and EY is equal to 1 by pi into the upper cutoff frequency and lower cutoff frequency FL to FH. The value is 1 psi x of omega into d omega. Psi x of omega into d omega. Okay, and you can change this as in terms of the normal frequency 1 by pi into the integral FL to FH psi x of 2 pi f and d omega is equal to 2 pi into df, as omega is equal to 2 pi f. D omega is equal to 2 pi into df. 2 pi into df. Okay, my dear students. So here the pi and the pi get cancelled. Shortcut notation of psi of 2 pi f psi x. Let us take here psi x. Ey is equal to integral FL to FH 1 by, so 1 pi is get cancelled, there is no any 1, and the psi x of f into df. Okay, so this the Vy is equal to 2 into integral FL to FH psi x of f into df. Got it, my students? This is for the energy spectral density. Psi x psi of omega is equal to the squared magnitude of x of omega in terms of the frequencies. Then the properties of the energy spectral density. The properties of energy spectral density. The first property saying that the total area under the energy density spectrum is equal to the total energy of the signal. So formula we know E is equal to 1 by 2 pi the integral minus infinite to infinite psi of omega into d omega. Or in terms of the normal frequency, the total area under the energy density spectrum, that is integral minus infinite to infinite psi of omega into d omega, is equal to total energy of the signal E is equal. And second property, now only we derive the expression. If x of t of the input signal of input to the linear time invariant system with impulse response h of t, then the input and output of energy density spectrum function was related as psi y of omega is equal to the product of energy density spectrum and the squared magnitude of the transfer function. Got it, my students? And also, we know that the autocorrelation function and the energy density spectrum is a Fourier transformation space. R of omega is a psi of omega. R of omega is a time domain function and psi of omega is a frequency domain function. Okay, my students. Now you can see the power density spectrum or power spectral density. In this, what is a power signal? The power signal signals which is a finite and average power and the infinite energy. The previously energy signal means energy is a finite and the power is a 0. Then only we can call it as an energy signal. But in the power signal means the average power is infinite energy with finite average power and infinite energy is infinite. So power is in between of 0 to infinite, and in this the energy is infinite, then this signal is called infinite, and the signal is called the power signal, and the examples of the periodic signals. If it is energy signal, means energy is a finite, 0 less than E less than infinite, and power is a 0. Power is a 0, then we can call it as energy signal. Energy signal, and is a periodic signals. Periodic signals, and 0 less than infinite, less than P less than infinite, E is equal to infinite. The power signals, it is a power signal, and is a periodic signals. Periodic signals. So what is the formula here? The P is equal to limit t tends to infinite, 1 by t, the integral minus t by the t by 2, or the t, the squared magnitude of x of t dt. Squared magnitude of x of t dt. Okay, the energy is energy signal same. The power, there is an energy. The power is defined above is actually the mean square value of the time average of the squared signal. Thus, x square of t whole bar, nothing but the mean square value. The limit t tends to infinite, 1 by t, the integral minus infinite to infinite, squared magnitude of x of t dt. According to the Parseval's theorem, the power of a signal in terms of its Fourier series coefficient, that is in terms of harmonic components present in the signal. Mathematically, the P is equal to sum of n is equal to minus infinite to infinite, the squared magnitude of the Cn. This is for the Fourier series. In the energy density spectrum or energy spectral density, take the Rayleigh's theorem or the Parseval's theorem in the Fourier transformation. Okay. Let's see the proof. To get the sum of n is equal to minus infinite to infinite, Cn square. The energy signal, the squared magnitude of x of t, we can write in terms x of t and the x of conjugate of t. Substituting the power, the P is equal to limit t tends to infinite, 1 by t, the integral minus t by the t by 2, x squared magnitude of x of t is x of t into x star of t dt. Okay, my dear students. But in the exponential Fourier series, the synthesis equation. What is the synthesis equation? Analysis equation is there for the x of k is equal to integral minus infinite to infinite x of t e power minus jk omega naught t dt. Got it, my dear students? And x of t is equal to synthesis equation, sum of n is equal to minus infinite to infinite, get x of t, x of omega actually here, the x of k that I am taking as a Cn into e power as a n value, positive and negative exponential becomes here the positive j n omega naught. N omega naught. So x of t is equal to sum of n is equal to minus infinite to infinite Cn into e power j n omega naught. Got it, my dear students? N into t is also there, that t. Instead of k, you can take here this n simply. Now you can substitute the x of t, the synthesis equation, the power signal p is equal to limit t tends to infinite, 1 by t, the integral minus t by to the t by 2, integral minus infinite to infinite, the t by 2, the x of t and x star of t. X of t can substitute here as a sum of n is equal to minus infinite to infinite Cn e power j n omega naught. the omega naught you can take as a omega here, or otherwise you can keep omega naught into t x conjugate of t dt. Got it? This is only for the function of x of t from the Fourier series, exponential Fourier series and synthesis equation. Limit t tends to infinite, 1 by t, the function integral, the sum of n is equal to minus infinite to infinite, cn, we can write it in the outside. I take the another integral is a minus 1 t by the t by 2 function, x conjugate of t e power j n omega naught t dt. What model students? Now the limit t tends to infinite, 1 by t. See, actually the conjugate analysis equation x of k is equal to nothing but c of k or the c of n. Let this the function as a cn. The k is becomes here the n. Cn star, you can take the cn conjugate. Here the whole conjugate will get whole conjugate. Then it becomes of integral minus infinite to infinite x conjugate of t is equal to, not is equal to, e power minus, with this conjugate it becomes a plus j n omega naught t d cn star. So here the same thing, but the limitation is from minus infinite to infinite. Here the minus t by the t by 2 as a periodic signal. So this total function you can replace as a cn star. Okay, it is integral minus t by to the t by 2 x conjugate of t e power j n omega naught t dt. Sum of n is equal to minus infinite to infinite cn. This total function I'm replacing as cn star or cn conjugate in terms of the power here. And sum of n is equal to minus infinite to infinite cn. So write the cn in the sum of n is equal to inside cn and the cn conjugate. The cn is nothing but the x of k only, my students. So p is equal to the sum of n is equal to minus infinite to infinite the squared magnitude of cn. Since x of t is a squared magnitude, x of t x conjugate, here the cn and a cn conjugate. In your Fourier series, I explained this Parseval's theorem in terms of p is equal to sum of n is equal to minus infinite to infinite, the squared magnitude of x of the k is equal to x of k squared. Okay, both are the same here, my students. This is called the Parseval's power theorem, and so it states that the power of a signal is equal to sum of the square of magnitudes of various harmonic presence in the discrete spectrum. Discrete spectrum. Okay, my dear students. Now see the properties. Parseval's, not the Parseval's, Parseval's theorem is derived, and the power spectral density, the distribution of average power of a signal in the frequency domain. The previous energy spectral density means the distribution of energy signal in a frequency domain. Now the distribution of average power of a signal in the frequency domain is called power spectral density or power density spectrum. To derive the power spectral density, assume a power signal as a limit case of energy signal. Consider the power signal x of t is extending to the infinity as shown. The power signal means is a periodic signal. Periodically it is repeated. The sinusoidal signal for every time period of the t, it is repeating. Okay. Let us truncate this signal so that it is a 0 outside the interval of tau by 2 as shown in the figure. Here, the total is a time period we can consider minus tau by 2 plus tau by 2 is repeated the function. The signal xt tau of t is a finite duration, the tau, and hence it is an energy signal with energy E is given by E is integral minus infinite to infinite x tau of t squared magnitude. In terms of the frequency, the 1 by 2 pi, the integral minus infinite to infinite x tau of omega into d omega. It's a Parseval's theorem. And x of t, the Fourier transformation is x of omega, or x tau of t is also the Fourier transformation of x tau of omega. We are taking only the truncated power signal from minus tau by to the tau by 2. We write as minus tau by to the tau by 2 the squared magnitude of x of t. Is both are same here. So 1 by tau is a periodic signal, 1 by to the minus t by to the t, tau by to the tau by 2, the squared magnitude of x of t. And its frequency function is 1 by 2 pi into d omega. There is no any 1 by 2 pi for the normal frequency x of omega. Got it, my dear students? 1 by 2 pi. Here the minus infinite to infinite as minus tau by to the tau by 2 is a periodic signal. 1 by tau we can multiply here. So 1 by 2 pi, the integral minus infinite to infinite, limit t tends to infinite, the x tau of omega squared magnitude d omega as total function. This total function inside there is a s of omega. How? If the energy signal E is equal to integral minus infinite to infinite squared magnitude of x of t dt is equal to, in the frequency domain, the minus infinite to infinite, the squared magnitude of x of omega d omega. This squared magnitude of x of omega, what we replace as psi of omega d omega. So the energy spectral density, the area under the energy spectral density is equal to the energy signal E is equal. Here, as a tau tends to infinite, the square magnitude of x of omega by tau approaches to the final value. That is nothing but it is denoted as a finite value as s of omega. S of omega is called as a power density spectrum or power spectral density. The average power of this function P is equal to 1 by 2 pi. The P is equal to, you can write as 1 by 2 pi as integral minus infinite to infinite. Instead of psi of f, we leave the s of omega into d omega as a power density spectrum, energy spectral density. And in terms of the normal frequency, there is no any multiplication factor of 1 by 2 pi, the integral minus infinite to infinite, s of f into df. Okay. Otherwise, the average power from 0 to infinite means multiply the 2. 1 by pi, the 0 to infinite, 1 by pi into 2 into 0 to infinite s of f. Okay. The power spectral density of a periodic function is given by the s of omega is equal to 2 pi into the sum of n is equal to minus infinite to infinite cn square. Now only we derive the expression, the Parseval's theorem is multiplied with the delta function. If the delta function is multiplied, means the same function will get the delta of omega minus n into omega naught, even if it is shifted also. The alternately, the s of f is equal to, there is many multiplication factor of 2 pi, the sum of n is equal to minus infinite to infinite cn square delta f minus n into f naught. As we derive the expression, the psi y of omega is equal to the square magnitude of h of omega into psi x of omega. The same thing as s y of omega is equal to the power spectral density, the squared magnitude of h of omega into s x of omega. The power P is equal to 1 by 2 pi. Integral minus infinite to infinite. S of omega into d omega is a power density spectrum function as a first property. The area under the power spectral density function. The area under the power density spectrum function is equal to the average power of the signal P. What we define the energy spectral density also. The area under the energy spectral density function is equal to the total area, total energy signal E is equal to. And second property is taking off the convolution function on both sides for the output function and the input function. And the transfer function is a ratio between of the output and the input. This Sy of omega is equal to the squared magnitude of H of omega into Sx of omega. And we know the third property of energy density spectrum or the energy spectral density, there is a Fourier transformation pair. Fourier transformation pair in between the autocorrelation and the energy spectral density. Now here also, there is a Fourier transformation pair in between the autocorrelation function and the power density spectrum. Three properties are same for the energy and the power density spectrums. Got it, my dear students? Next, the difference between comparison of energy density spectrum and the power density spectrum or spectral density. First point is it gives the distribution of energy of a signal in frequency domain. Energy of a signal in frequency domain. The power spectral density means it gives the distribution of power of a signal in frequency domain. It is given by the psi y, psi of omega is equal to squared magnitude of x of omega. And it is given by the S of omega is equal to S of omega is equal to, because it is a periodic signal with a period of tau, limit t tends to infinite 1 by tau, the squared magnitude of x of omega. It's a periodic signal, is a periodic signal. So apply the limit t tends to infinite 1 by t. The total energy is given by E is equal to 1 by 2 pi the minus infinite to infinite psi of omega into d omega, or integral minus infinite to infinite psi f of omega into d, psi of f into df. In the power, total power is given by the area under the frequency domain function s of omega into d omega. The power density spectrum 1 by 2 pi into integral minus infinite to infinite s of omega into d omega, that is equal to integral minus infinite to infinite s of f into df, where s of f is power density spectrum or power spectral density. Psi of f is energy density spectrum or energy spectral density. And both are related with the autocorrelation function only. It's a Fourier transformation pair. Autocorrelation function for the energy signal and its energy spectral density form a Fourier transformation pair. And in the power density spectrum or power spectral density, the autocorrelation function of a power signal and its power density spectrum form a Fourier transformation pair. Fourier transformation pair. Now let us see the Fourier transformation pair, the relation between autocorrelation function and the energy or power spectral density function. The last one. The last point for the two comparisons, we are saying it is a Fourier transformation relation. Let's see the Fourier transformation relation we get or not. R of tau is a psi of omega. We know the R of tau autocorrelation function, integral minus infinite to infinite. What is the formula? I have to remember that one signal is a normal signal, another signal is a delayed version. X of t minus tau dt. Take the conjugate. Any one is a conjugate. And the R of tau is equal to, you can replace the x conjugate of t minus tau by its inverse transformation function. Inverse transfer function. So the R of tau is equal to integral minus infinite to infinite x of t into inverse Fourier transformation formula 1 by 2 pi integral minus infinite to infinite. The signal is x of omega. The inverse Fourier transformation of this signal means x of omega into e power as a positive value j omega into t minus tau d omega. Okay, instead of t is there x of t. This total signal is x of. Got it, my students? Otherwise, the t minus tau is a t minus x of t minus tau. So, what is the x of t? Inverse Fourier transformation 1 by 2 pi integral minus infinite to infinite x of omega into e power plus j omega t into d omega. This is a formula for the inverse Fourier transformation. Now, using this relation only, instead of t, they replace the t minus tau. T minus tau, I replace the t minus tau. And the conjugate is there. So, the r of tau is equal to integral minus infinite to infinite x of t whole multiply with 1 by 2 pi. I take the conjugate inside the integral minus infinite to infinite x conjugate of omega, and now the positive exponential becomes a negative e power minus j omega t minus tau d omega. Okay, and interchange the integrations here as x of omega integral minus infinite to infinite x conjugate of omega and integral minus infinite to infinite and 1 by 2 pi you can write in the outside. The x of t, x of t, right here the e power minus j omega t. Here there is a dt is also there. You can write all the terms is a dt is multiplied. Here the dt also. We replace only the x star of t minus t. Dt is there, and here also the dt. E power minus j omega t, and use this dt here. Another function, e power minus of minus is a plus. E power j omega tau d omega. Got it, madam? Now, what is this function totally? Is a Fourier transformation definition on integral minus infinite to infinite x of t power minus j omega t dt. So 1 by 2 pi integral minus infinite to infinite x of x conjugate of omega, and this function is x of omega into e power j omega tau d omega. So we know the x conjugate x star of omega x of omega is squared magnitude of x of omega. So the r of tau is equal to 1 by 2 pi integral minus infinite to infinite. You can write as a squared magnitude of x of omega into e power j omega tau d omega. What is the squared magnitude of x of omega is nothing but energy spectral density psi of omega into e power j omega tau d omega. R of tau is equal. So now we can observe here the x of with this formula, the inverse Fourier transformation to this 1 by 2 pi, the integral minus infinite to infinite instead of x of omega. Now here the psi of omega. If these two are x of t is a Fourier transformation pairs. Now here r of instead of x of t is r of omega, r of tau, and x of omega psi of omega. Therefore, the r of tau is Fourier transformation pair of psi of omega. Okay, is inverse Fourier transformation form. This proves that the autocorrelation function and the energy spectral density or energy spectrum or energy density spectrum is a Fourier transformation pairs. Got it, my students? Now, the similar way, the relation between autocorrelation function and the power spectral density is also the Fourier transformation pairs. That is, R of tau is equal to sum of n is equal to minus infinite to infinite Cn and Cn minus e power j n omega naught tau Cn square here. Now you can apply the Fourier transformation on both sides with this Fourier transformation. This is a formula for the frequency domain function, Fourier transformation relation. The Cn square e power j n omega naught tau, and you can multiply the e power, not the multiply, the Fourier transformation formula itself. So this is a x we can consider integral minus infinite to infinite x of t into e power minus j omega tau. X of omega is equal to the Fourier transformation formula x of t into e power minus j omega t dt. Instead of t, here the tau is there, integral minus infinite to infinite, that's r of tau e power minus j omega tau dt. This is x of omega actually. Okay, what is r of tau? We have the minus infinite to infinite, the sum of n is equal to minus infinite to infinite and e Cn square squared magnitude e power j n omega naught tau is r of tau is equal to, we got r of tau is equal to, and e power minus j omega tau d omega. Let's simplify this function to get the inverse Fourier transformation of r of tau. This is Fourier transformation of r of tau. This equation is for the Fourier transformation of x of t, because instead of x of t, I am taking the r of tau. Okay, so sum of n is equal to minus infinite to infinite, a squared magnitude of Cn square, Cn. Write the integral minus infinite to infinite, e power, both are exponentials only. Take the minus j, tau is a common, omega minus omega naught into n omega naught d tau. Got it, my students? So this integral of e power minus j tau exponentials, integral of exponential can represent as a delta function. The 2 pi into delta function. The sum of n is equal to minus infinite to infinite, magnitude square, and this exponential we can write as a delta of omega minus n omega naught. 2 pi into delta, the one with the Fourier transformation. Here the one is there, e power j omega. The Fourier transformation, one Fourier transformation is 1, the Fourier transformation is 2 pi into delta omega. 2 pi into delta. What is that? X of omega is equal to integral minus infinite to infinite. X of t is a 1, e power minus j omega t dt. This is a formula, e power minus j omega t. J omega t, instead of omega, here the omega minus n omega naught. So I use here the delta omega as omega minus n omega. Got it, my students? It's a Fourier transformation of r of tau is equal to the Fourier transformation of 1 we can replace here 2 pi into delta of omega. Okay, in the normal frequency there is no any 2 pi. The sum of n is equal to minus infinite to infinite squared n, and this delta function as a delta of f minus n into f naught. Got it, my students? So the Fourier transformation of this, the RHS is the power spectral density. The total RHS is a power spectral density. Here, this one. So Fourier transformation of r of omega is equal to s of omega, and there is a relation between S of omega and R of tau is a Fourier transformation relation. Fourier transformation relation. Or Fourier transformation pairs. Got it, my students?